Hello and welcome back to Miles Maths. This is the third video on transformations of graphs, and this one's on reflections of graphs. For this one, we're going to use a rather more interesting graph than we've used before. Rather than using y equals x squared or y equals x cubed, which we've used in some of the other videos, we're going to use y equals root x. This function leaves itself. It's very useful. It's very good for seeing reflections. Now, to summarize what we know so far. If whatever we're doing to the function, be it a translation or a stretch, which we've already seen in the previous two videos, if it's outside the function, that's whatever happens is in the y direction. If it's inside the function, it's in the x direction, and that's no different when we come to reflections. The rules are maintained. So, to begin with, let's have a look at y equals minus root x. Well, y equals minus root x is literally a reflection of y equals root x, but it's reflected in the x-axis. So it's reflected in the y direction. That's the thing we've got to remember. It's the y direction. And that's what leads the commonality to all of these transformations of functions. If, however, we look at y equals root of minus x, we see it's a reflection in the y-axis, so it's in the x direction. And you've got to think about the direction it's going in. So we'll see it's in the x direction. This is the same for all functions. So let's pick a function that looks like y equals x squared minus 3x minus 4. Beautiful parabola. What are we going to see then? If I put a minus in front of the whole thing, I put the whole function in brackets, I put a minus outside it, are we expecting it to be in the y direction or the x direction? Well, the minus is outside of the function, hence it's going to be in the y direction. So we're expecting this to flip in the x-axis and end up being completely the other way up. And it is. What do we notice? What we should notice here is there are two invariant points, and as with stretches, the invariant points are going to be on the x-axis because we're moving in the y direction. We're reflecting in the y direction, so the invariant points are on the x-axis, and we just flip it over. If, however, we're taking the negative inside the function, so rather than x squared, I have minus x all squared. Rather than x here, I have minus 3 times minus x. Here we have minus 3 times minus x. You notice the minus x is in brackets. Still got the minus 4 on the end. Then we're going to expect to see this in the x direction. And we're going to expect to see the invariant point on the y-axis. So the invariant point doesn't change. So it's just a point that doesn't change. That's all invariant means. So we can see that the line of symmetry is the y-axis. In other words, the reflection has happened in the x direction. So we can see that this point here is now here, and this point over here, positive 4, is now over here at negative 4. So here is, and this is the sort of typical way that the questions are phrased, here is a y equals x cubed minus 3x squared minus 1. Could you sketch the graph of minus x cubed minus 3x squared minus 1 all in brackets? Of course you could, because you know that the negative is outside the function. Hence, if it's outside the function, it means we're going in the y direction, which means I'm just going to flip the whole thing upside down. So any point, if I see a point here that's at minus 1, I'm going to move that point to 1. If I see a minimum down here at 2 minus 5, I'm going to move that to 2 plus 5, and there's going to be a maximum up here. And I flip the whole thing upside down, and there it is. And we notice that the invariant point, and there is an invariant point, is on the x-axis because I'm working in the y direction. So there's the invariant point. If, on the other hand, I take the minus inside the function, as I have done here, so I have minus x all cubed minus 3 times minus x squared minus 1, then this is going to be working in the x direction. The invariant point will be here on the y-axis. This point here that's at 2 minus 5 will end up at minus 2 minus 5 because it's in the x direction. And there it is. There's my invariant point, and I can see that I've just reflected it. And that's reflections. They're quite easy. However, the trick here is to remember that very often they will, as you'll see when I do some questions, they expand these brackets, which make it slightly more tricky.
Okay, let's look at some worked examples on reflecting graphs. E.g. 1. Here is the graph of f of x equals x squared minus 8x plus 7. There it is. Sketch the graph of f of minus x. So, f of minus x, the minus is inside the function. So we know that this is working in the x direction. So what I can see here is this is a reflection in the x direction, and anything on the y-axis is an invariant point. So this point here at 7 will be invariant. However, everything else will reflect. So this point here at 1 will reflect to minus 1. This point here at 7 will reflect to minus 7. This point here, the minimum point, which is at 4 minus 9, will become minus 4 minus 9. And so on. Here I have a point which is at 5, 6, 8, which is at 8, 8, 7. So this will become minus 8, 7. So I can kind of get an idea of where it reflects to. Even if you don't have an exact grid to do this on, if you're reflecting a graph that's already there, you can kind of use the basic scale of things to kind of work out where things have got to go. So this will come down something like that, down to the minimum point, and then up. And there we go. First part done. Sketch the graph of minus f of x. Okay, so now the negative is outside the function. It's outside the function, therefore this is a reflection in the y direction. So now I'm reflecting in the x-axis. Any points that are on the x-axis will be invariant, so it will go through those 2 points. This point's at 4 minus 9, so this point will be at 4, 9. Because remember, the whole thing is now going to flip upside down. The y-intercept, which was here at 0, 7, well, that's going to reflect through. So we're going to go 7 out the other side, and we're going to go to 0 minus 7. Similarly, this point here, which was 8, 7, is going to get 8. It's going to be 8 minus 7, which I think is there. And we should now be able to kind of just sketch this in. As I've said on the other videos, obviously you would do this in pencil because that's what GCSE tells you to do. I'm doing it in pen just because it's more visible. So here we have the graph of minus f of x. It's outside, the negative is outside the function, it's flipped in the y direction. Here the negative f of minus x, the negative is inside the function, therefore it's reflected in the x direction. Second example. F of x equals x squared minus 4x plus 8 has a minimum point when x equals 2. Circle a sentence which is true. Okay, so this is a different looking question. So one of these sentences is true. All I have to decide is which one. So this has, I'm going to sketch this thing. So so what I know is I don't know where this minimum point is. I could work that out, of course, very quickly. I might do that. I might actually say, well, what's f of 2? F of 2 would be 2 squared minus 4 times 2 plus 8. So this is 4 minus 8 plus 8, which is 4. Of course, so this is at the point 2, 4. So if I were just to do a quick sketch of this thing, what would it look like? Because that'd be quite interesting. When x is 2, y is 4. So x is 2, y is 4. This has a minimum point like this. It goes through 8. It's quadratic. That's pretty awful, but never mind. So, minus f of x, does that have a minimum point when x equals 2? What does minus f of x look like? Well, I know it's a reflection in the y direction because the negative is outside of the function. So would it have a minimum point? Well, it would look like that. So it can't have a minimum point. Can minus f of x have a maximum point when x equals 2? Well, this is obviously when x equals 2. So would this be reflected to down here? Yes, it would. In fact, this is minus f of x. That's what it looks like. Yes, it would have a maximum point when x equals 2. That seems to be true. Let me just check the others though. F of minus x. So what does f of minus x look like? Well, f of minus x I know is a reflection in the x direction, and I know that that would be somewhere over here. So so I know that would have a minimum point somewhere over here. So this would presumably have f of minus x would presumably have a minimum point when x was minus 2. So this one's clearly not true. This one's clearly not true. F of minus x wouldn't have a maximum point, no, when x equals 2. So this one's clearly wrong. So clearly the answer, as we thought, has got to be this one. That minus f of x, there's minus f of x, has a maximum point when x equals 2. But you can see how sketching the graph helps me to answer the question. So the graph sketching is quite important. Here's a third example. Well, it's a very similar sort of idea. Look, f of x equals x squared minus 3x plus 1 is reflected in the y-axis, which reflected in the y-axis to give g of x. Circle the expression which represents g of x. Okay, so it's reflected in the y-axis. Right, let's just underline that. What does that mean if it's reflected in the y-axis? Well, if it's reflected in the y-axis, that means it's a left-right reflection, which means it's in the x direction. If it's in the x direction, is the negative inside or outside the function? It's inside the function, isn't it? Okay, so what I want to do is I want it to be, instead of x, I want to put minus x in. So minus x squared minus 3 times, okay, so I want this inside the function, so minus x. So wherever there was an x, I'm putting a minus x plus 1. Really, this is what I've done. I've done f of minus x. And all I want to know is, one of these 4 expressions here is the same as this. So I've just got to do a bit of simplification. Minus x all squared, well, minus x times minus x is, of course, plus x squared. Minus x times minus x is plus x squared, so just x squared. Minus 3 times minus x is plus 3x, because we've got the minuses there. And we have plus 1. So x squared plus 3x plus 1. That's that one. There we go. So once again, just even sketching a set of axes helped me think that problem through. A function has a turning point at minus 1, 4, which is shown there. Look, that's very good. As shown on the graph. Lovely. Find the coordinates of the turning point of the function minus f of x plus 3. Okay, so what we're going to do is we're going to do this in 2 stages. We're going to consider what minus f of x would look like, and then we're going to translate it. So this is f of x, presumably, and I want minus f of x. So what does minus f of x look like? Well, the negative is outside the function. Therefore, this is a reflection in the y direction. So it's a reflection in the x-axis. There are no invariant points because we don't cross the axis at any point. However, if this is minus 1, 4, that point must reflect down to, presumably, minus 1, minus 4. So I could just sketch that in. And I could just label it, this is minus f of x. But I want minus f of x plus 3. So I'm now going to take this curve and I'm going to move it up 3 places. Am I going to cross the axis? Well, no, not quite, because -4 is going to leave me here. It's going to leave me at -1, -1, in fact, because I'm moving it up 3. And I would end up with a curve that looked like that. This is the turning point, so it's simply -1, -1. Find the coordinates of the turning point. Answer -1, -1. Job's a good one. Now, it didn't again ask me to sketch the curve. It did give me a graph, it did encourage me to do that, but it didn't tell me to. However, drawing it, sketching it, is going to be a massive help to actually answering the question they want you to answer. And that's it.